On March 2025, we began our study of the Yokohama Landmark Tower. The Yokohama Landmark Tower was a captivating structure. We studied its architectural background, the architect's intent, and its symbolic meaning, ultimately realizing that it was a product of Japan's economic growth. We also learned that the tower was part of a TOD-centered development based around Minatomirai and Sakuragicho stations. Minatomirai Station, Queen's Tower, Landmark Tower Plaza, and Sakuragicho Station are all connected on Level 2, an elevated circulation system designed with the movement along the King, Queen, and Jack axis in mind. The connection between the subway station and Queen's Tower gave rise to the Grand Escalator, which functioned as a station core. The Yokohama Landmark Tower and its surrounding buildings functioned as urban cores reflecting horizontal circulation. This was particularly notable as the design incorporated considerations from transportation engineering. We then moved on to examine the construction process in depth. The construction sequence of our building followed this order. The site was prepared through ground leveling and slurry wall construction, forming the underground diagram walls. Excavation was carried out afterward. Steel formwork for backfill concrete was fabricated in preparation for the mat concrete placement. After the blinding concrete was poured, rebar placement followed. The mat concrete was constructed as a reinforced concrete structure. The mat foundation rebar was connecting using couplers, staggered, and distributed rather than concentrated in one area. The rebar diameter was approximately 15 mm. After placing the bottom rebar, steel bar chair frames were installed for the upper rebar, which was then laid on top. These bar chairs were spaced at 6-meter intervals, with steel columns and beams installed accordingly. Concrete pouring followed, during which hydration heat control became a major concern. Low heat concrete was used, and hydration heat was controlled through embedded cooling pipes. After the mat concrete was poured, construction of the underground and above-ground structures began. Bolted connections were used to link the upper part of the mat concrete with the steel structure, and a steel reinforced concrete system was employed. While studying this building, we read numerous papers and articles, and even traveled to Yokohama for on-site research to identify key issues. Seeing it with our own eyes, we were struck by the building's towering height and its unconventional floor plan. As we ascend floor by floor, we noticed the repetition of star-shaped spaces and began to wonder how these forms were stacked and constructed. In this session, we aim to answer that very question. Today, we will explore the typical construction sequence of a single floor in the Yokohama Landmark Tower, from the stacking plan to the steel structure, beams, slab, and finishing works. Up to the 9th floor, a steel-reinforced concrete structure was employed to withstand the heavy loads. Above that, the remaining floors are constructed entirely with a steel frame structure. In the Yokohama Landmark Tower, adopted a dual-tube structure consisting of a central core and surrounding steel frames. By applying core-first construction, structural stability was secured in advance, even before the steel framework was erected. Therefore, the steel frame was not required to bear the entire load, nor was it necessary for it to do so. This made it possible to install 3 upper floors even before the lower floors were completed. When the core is created, the steel structure is lifted. A column, that is, a steel structure, is erected to start the lamination. A 3-story steel structure is made in advance. There are various reasons for making multiple layers of structures in advance. The first reason lies in the advantage it offers for fabricating complex structural forms. Yokohama Landmark Tower has a tapered shape. Therefore, the internal columns of the low layer were designed to maintain verticality, and the steel, which is the external column, was designed to tilt about 4 degrees. Looking at the plane, columns has a complex structure that requires precise welding and bonding, such as 165 degrees and 19 degrees. Therefore, it was advantageous to make it on a stable ground, not on a high site. Each structure is superimposed through a crane. After that, the structure is positioned by bolt joining. This procedure was performed once every 3rd floor. The second reason was to ensure better control in responding to potential deformation or failure of the steel structure. Our building features a dual-tube structural system. The outer columns were responsible for carrying 60% of the building's total load. Under wind loads, shear lag causes greater forces on the outermost columns. Such heavy loads can lead to bending or failure in the columns. Steel structures face the following issues under heavy loads, tension, or repeated stress. Columns may experience buckling due to compression and slenderness, while joints and bolts are vulnerable to brittle failure or fatigue from repeated loading over time. These are the specifications of each primary load-bearing column in our building. When calculated based on the 3-story module, the columns show the slenderest radius. Given that the Yokohama Landmark Tower is a super tall building located in a seismic zone, It follows a much more conservative slenderest limit than the standard 200. Reducing column height lowers the slenderest ratio but increases the number of bolted joints. Connections between columns made by bolts and welds are vulnerable to brittle failure. Thus, the 15-meter, 3-story columns was an optimal size to prevent buckling and brittle failure. Third, as the building rises, the load decreases, allowing the columns to become thinner. The columns were reduced within the limits of the strong column weak beam principle, and the 3-story system provided a good rhythm for this adjustment. Fourth, it was for construction efficiency. Crane operation was limited, especially in the upper floors where constraints were even greater. Each floor contained over 200 columns, girders, and beams. The 3-story structural stacking allowed each floor to have its own process, creating a construction cycle. There were also practical limits in fabrication and transportation. It was the most practical size to optimize factory productivity and ensure safe, efficient transport to the site. Unlike other systems, steel structures are manufactured under strict quality control in factories, resulting in high material uniformity. This ensures excellent predictability in load and deformation, leading to greater design reliability. The first step is constructing a typical floor is positioning the steel structure. Prefabricated components are lifted into place using a 1,500-ton crane. Since the H-beams are not primary load-bearing columns, they were joined at the column splice with bolted cover plates. Square and circular steel tubes had to maintain closed sections to function as CFT columns. When beams were connected to the steel tubes, stresses from the flange and web were directly transferred to the tube walls. Internal stiffeners were used to reinforce the joint and ensure sufficient strength. The second step is the installation of beams and girders. To transfer loads to the core and outer columns, main girders were first connected directly to the center RC core and parameter columns, followed by the installation of beams between the columns. When the connection points of the outer steel beams align with the embedded plates, final fastening is completed using high-strength bolts or welding. This connection method enables composite action between reinforced concrete and steel, maximizing the building's overall lateral stiffness. The third step is slab installation. Before pouring concrete, factory-made deck plates are placed. The edges and joints of the deck plates are secured to beams, girders, and adjacent plates using dedicated stud bolts. Laid over beams and girders, the deck plates support the initial load during concrete pouring and serve as temporary formwork until the concrete cures. For interior columns and walls, concrete was poured using conventional formwork. The final stage involves the exterior wall, MEP systems, and finishing works. The Yokohama Landmark Tower's facade was manufactured in 3-story modules at the factory and assembled on site. Finishing of piping, electrical wiring, and other utilities were carried out after all structural and enclosure work have been completed. Each floor was constructed in this sequence, and through this repeated process, the Yokohama Landmark Tower was built. The floor plan of the 51st floor was somewhat unique, as it served as the outrigger level for structural stability. More steel structural members than usual were lifted and installed as outriggers within the mechanical floor. The 51st floor was determined based on structural stability calculations for the dual-core system, and an outrigger was installed to maximize resistance against lateral forces such as earthquakes and strong winds. Inside the core, key components of the outrigger system include the upper chord, lower chord, and vertical members. These members are connected to the columns and beams of the outer tube through diagonal braces, establishing a mechanism that efficiently transfers forces from the core walls to the perimeter structure. The upper chord has stud bolts welded at regular intervals along its sides to enhance composite action with the concrete, and the lower chord is also reinforced with welded stud bolts. The upper and lower chords, along with the vertical members, are steel columns embedded within the core walls. The outrigger diagonal braces connected to the inner core are fabricated in 2 segments. The first segment is located at the lower part and is connected to the outer tube column. The second segment is located at the upper part and is welded to the joint of the upper chord inside the core wall. The upper connection is constructed using a delay joint method. This means that final welding is performed only after the initial deformation of the concrete has stabilized, in order to minimize residual stress and ensure structural stability. We have explored how each floor of the Yokohama Landmark Tower was stacked and completed, revealing the harmony between architectural aesthetics and cutting-edge engineering.